All right, recording is rolling. It is Monday, April 29. We're gonna continue this quantum mechanics adventure. So number 12 through 16 on your journals today. All right, before I dive too far into that, let me switch my screen over here. So this morning on Google Classroom, I posted a schedule related to final exams. So it says seniors, but here, let's take a look at this. So um, on May 15th, a couple of weeks from now, seniors take their first exam. That's for English and math. It'll be on Wednesday the 15th. Right. On Thursday the 16th is for social studies and science. Right. I do have a few seniors among all my classes, so we will have finished the final exam review by then. So you guys be ready to go. Right. And then Friday the 17th is the very last day for seniors. The week after that is, well, no more seniors, all gone. And then final exams there. Yeah, we're getting right down to the end. That's about the schedule we're looking at. Want to go get another look at that. Again, that's posted on Google Classroom. All right, so give you guys a recap of what we've seen so far. We've been working on this a few days. So near the beginning of the story was the photoelectric effect. It goes back to 1887. So it was known that light had wave properties, but Einstein interpreted this experimental data as light also has particle properties, right? That would explain this direct relationship between the energy you get from light and the frequency of the light. Right? It has some kind of particle property called photons. Right. The slope of this line, h, is called Planck's constant. Right, it's a universal constant in nature. Nobody knows why it is that number, but it's certain to be that. There's Planck length and Planck time, the smallest units of length and time you can reasonably talk about in physics. Right, so de Broglie comes along and says, hey, I wonder if that dual nature that applies to light, I wonder if that applies to anything else. Can you have, say, like a wavelength of a particle, take Planck's constant, divide by the momentum of the particle? And okay, if you could do that, what possible practical application would that have? Well, how about the entirety of chemistry? Is there this electron configuration? Why do electrons occupy certain orbital spaces? Why is the entire periodic table organized the way it is? Why does any chemical reaction happen? It all ties back to this wave nature that electrons have. Schrodinger wave equation can describe where is an electron going to be. Now, in macroscopic physics, you can describe, see, for any particle, say it has like some mass and some location and possibly some speed and maybe an acceleration. You can put that all in an equation. You can determine exactly where and when it's going to be. Now, in quantum, it's a lot trickier. You run into, well, this probability function, and also that goes hand in hand with this Heisenberg uncertainty. Right? You can't know exactly where something's going to be. But back to Schrodinger here, the best you can do is come up with a probability equation. Now, a week or two back, I was showing you guys normal distribution curves, which kind of looks like that. It looks like a normal distribution curve. The Schrodinger equation, think of it kind of a fancier version of that. So where's an electron going to be? Well, it's probabilistic. You could measure it 1,000 times and then make like a bar chart, and it's going to approach, say, something that looks kind of like this, and you could describe it mathematically like this. Okay? Now, interestingly, when you make an observation, an actual measurement, where's the electron? It actually does more definitively show up in one place. I guess most likely it would show up there, but yeah, maybe sometimes it'll show up there, and every once in a while, maybe it'll make 1,000 observations. Sometimes it'll show up, say, in one of these tails, right? And then this entire wave function just collapses and it recenters around your last observation, right? So the act of measuring, observing, actually affects reality. Right? It goes hand in hand with something called the measurement problem, right? All right, so Heisenberg uncertainty, there is a limit in the universe, fabric of the universe, when you get too small. Can you know precisely where a particle is going to be and also its momentum? Well, no, you run against this limitation. You guys saw an actual experiment, shine a laser through a slit, right, to run into that limitation there. Right? So a double slit experiment. Right? So here I've got this electron, but it could be a photon. If you take some subatomic particle, some fundamental particle, shine it through a double slit, it'll create an interference pattern. Okay, great. So it's a wave, right? Well, unless you get too much detailed information about exactly which slit did it go through, right? And that collapses the Schrodinger wave equation. It goes back to behaving like a particle, right? So this is hand in hand with that Schrodinger equation story. Now, back in probably about 1930s, Erwin Schrodinger was looking at all the crazy physics that's coming out of quantum experiments and saying, there's no way some of this stuff could be real, because here I can make up an example of that would be like counterintuitive to our macro experience. Okay? So can you take the quantum world and relate it, tie it to like the kind of like the classical physics macro world? So, for example, radioactive particle has some half-life. Suppose the half-life was like 1 hour, right? Well, that means after 1 hour, come back and check on it. There's a 50-50 chance it's decayed. Come back an hour later, right now, chance gets cut to half an hour, so 75% chance it's decayed by that point, and so on, right? Right. But while you're not observing it, you have to describe has it decayed or not as definitive, but as probabilistic. Right? Right, so it exists in a state of superposition. Right? Now, if that triggered this chain reaction of, say, once it decays, spits out a particle, and say, like, opens this vial of poison, which kills the cat, right? Well, if this is all in a closed box and this outside observer has no way of seeing inside the closed box, then you have to describe this entire process as also being a state of superposition. So it's not that the cat is dead or alive, it's that the cat is in superposition of being dead and alive, right? Okay, we're getting up to where, right? So we're not quite ready for this one yet, but I'm gonna give you guys notes on this one, and then switch over, roll some videos. Right, so what is quantum Zeno? Right? So these last few ideas kind of go together too. Make a graph here. Right? You guys got rulers on your desk? You guys make a graph? Okay. So let's talk about radioactive particles. So say I got this radioactive particle. So there's like an atom. Maybe I'll drill a little trefoil here. Right, it's like radioactive, right? Which means, right, so has some half-life. After some time, it's gonna decay into something else. On the vertical axis of this graph, I'll say probability of decay. And horizontal axis could be like time, something like that, right? Right, so yeah, suppose this atom had a half-life of 1 hour. I was using a chain foil in Schrodinger's cat, say like a radioactive atom. Okay. So if you check on it after 1 hour, there's a 50% chance that it's decayed into whatever it's going to decay into, right? 50%. Right? If you leave it alone and come back an hour later, right? So suppose it hadn't decayed after the first hour. Well, next hour there's another 50% chance, right? So now, since time is 0, now we're up to a 75% chance that it's decayed, right? Suppose it still hasn't decayed. Leave it alone, come back another hour. Now it's up to like 88% chance it's decayed, right? If you let the clock run, say 100 hours, at that point, there's something like a 99.9 something percent chance it's decayed. If you have like millions of particles, maybe only a few of them have it by now after like hundreds of hours, right? But funny thing, if you keep constant observation on this radioactive particle, here, make a note down here. So with observation, if you have some kind of observation equipment, right, the wave function, remember Schrodinger's wave, right, continually collapses back to its original state. And so radioactive decay never happens. Okay. So you guys are finished to write that down, right? To keep some kind of detection equipment on this otherwise radioactive atom, say it has a half-life of 1 hour, okay? But you're constantly monitoring it. So like maybe like 60 frames per second, just constant monitoring, okay? That probability of it ever decaying, right, keeps recollapsing back to the original state, right? This is back to the measurement problem. By observing, right, you're actually affecting reality, right? But like a nose being washed, right? And so after 1 hour, it doesn't decay. You say, okay, well, there's only 50-50 chance it would have anyway, right? You wait 2 hours, still hasn't decayed. Oh, okay, well, 25% of chance this would happen randomly anyway, right? 3 hours, 4 hours, 5 hours, right? And sitting and watching this thing for 100 hours and it just not decaying. Well, it's definitely had to by now, right? But not if you are constantly monitoring. All right, so dig up some videos for you guys. Find. All right, there you go. There's quantum Xeno. Right, next one, quantum tunneling. All right, my computer's frozen. All right, time out. We're gonna wait for my computer to stop being frozen. Ooh. All right. Here then. All right. So yeah, you guys remember our normal distribution curve from a couple weeks ago, right? So taking quantum, and I guess Schrodinger wave equation, I guess be maybe closer application here. Okay? Like, where's a particle going to be? Well, there's a probabilistic answer to that. Okay? Now, also you showed like a probability cloud. Right? So say like, where's the electron? Now, if you observe it, measure it, right, you'll get more definitive answer. Right? But before that, the best prediction is just this probability cloud. So it's probably somewhere kind of near the middle, right? And then as you get further out, there's maybe less and less likelihood, right? And maybe there's no like hard edge to this, just kind of tapers out. It's kind of fuzzy here, right? And what if there's like a barrier? Say, well, it normally couldn't cross this barrier, right? Maybe like, hey, maybe like two hydrogens don't want to be together to make helium, right? That fusion wouldn't want. It's hard to make that fusion happen, right? But every once in a while, just because of this tunneling, um, phenomenon, right? It's like maybe here, right? Sometimes the particle shows up on the other side, right? So what's the practical application of this? So it helps explain. Well, one practical application could be electronics. Right? Say like computer chips. If you look at Moore's law, right, the number of chips that you can economically fit onto what number of transistors you can fit onto a chip economically, like periodically doubles, falls like a either an exponent or a log function, right? Depending on which way you think about that. Right. But will Moore's law continue forever? Can you just keep making smaller, smaller electronics? Well, at some point you're running up against the fundamental like aspects of the universe, right? So what if you wanted to use an electron to represent a bit, like a 0 or a 1, right? Well, if you get too small a particle in too small confined space, you're going to run into this tunneling problem where sometimes a 0 flips to a 1 or vice versa, right? You mess things up. And so yeah, so that's going to limit like how small, say, like computer chips or electronics could be. All right, the other example we went with is fusion in the sun. Okay. So we say, what's the temperature and pressure at the middle of the sun, and then run the math on that. Should there be enough fusion that would be explained to explain how bright the sun is? Well, it doesn't quite add up unless you also include this tunneling effect, and then you have everything you need to explain how bright is the sun due to nuclear fusion. Okay. And so there you go, quantum tunneling. All right, you guys ready for entanglement? All right, so quantum entanglement. Ooh, I got this fancy looking poster. Now, this, about to roll you guys a video that's about 9 minutes long, takes some really deep thinking. So here, lay this out here and then we'll go to this. Okay. So you guys remember angular momentum and conservation of angular momentum? So like you have an ice skater spinning, pull their arms in, whoop, speed up spinning, whole deal. Okay. So angular momentum is conserved. What if you have two particles that both say like a particle pair out of nothing, right? And one property of particles is that they're spinning, but they have to have opposite spins so that angular momentum is conserved. If you started with zero angular momentum, you have a pair of entangled particles. They still have zero net angular momentum, right? Okay. Now the funny thing about electron spinning or small particle spinning is that their spin is not clearly defined. It's not like a baseball spinning where there's a clear axis, right? It's that the spin is probabilistic. So which way is it spinning, right? Now start from there, and there's this really bizarre outcome from just that very simple beginning. Okay? That well, Einstein's eventually going to confirm spooky action at a distance. So quick for that. All right, so let's flip over and see explanation for quantum entanglement. We're going to be looking at spooky. Ooh, all right. All right, so that was pretty hefty. Walk you guys through that again. Okay, so we've got this pair of entangled particles, and I'm going to start with what if you have two detectors that are oriented the same way, right? That's probably how they started doing this, right? And what they noticed is that the spin of the particles was always opposite. So if one was spin up, the other was spin down, right? Even if you separate these two detectors by 1 light year, right? You let the particles travel for like a whole year, some crazy distance, right? Oh, right. Once you know the spin of one, the other immediately becomes the opposite, which is weird because if spin was only ever probabilistic, that well, it seems like there must be like some information traveling from one to the other to indicate that, and that would have to travel faster than light, right? Right. Well, Einstein thought, no, there's no way that could be. But what's probably actually going on is that there's some kind of hidden information we're not aware of that's so that it's producing this effect, and it looks like they're communicating faster than light, but really it was determinable all along. It's not really probabilistic, right? So how could you test that? Because in science you're trying to disprove ideas if you can. You can debunk ideas, right? Right now, Einstein died in the 1950s, so this John Bell experiment wasn't done until 1964, so this is a little after Einstein. But this is the experiment they set up. Said, hey, what if I have these detectors that, okay, now we're going to bring out the 120 degrees, okay, 120 degree triple detectors going on, right? He says, well, no, if the detector is measured in the same direction, then they're always opposite. So I've got that set up, right? But what if you measure like this detector against this detector, maybe something like this, right? And then, so if there's hidden information, so on this poster, everything in this blue box is starting with Einstein's hypothesis, like that there would be hidden information. What would that actually look like, right? So it could be that you got opposite, 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 and then no matter how you pair these, so 1, 2, 3, 4, 5, 6, 7, 8, 9, nine different ways you can measure this, they would always be opposite that way, right? Or maybe it's like this. Maybe it's like spin down, up, and up, and then up, down, down would be opposite that. So you could go 1, 2, 3, 4, 5, 6, 7, 8, 9, get these 9 different experiments, right? So you have an odd number of experiments, and 5 out of 9 times with that alignment, they would be opposite spin, right? So you can interpolate between these two and say, no matter what the hidden information might be, if it looks more like this, right? You can make up any crazy example of hidden information. It's always going to fall into one of these two categories. Okay? Interpolate between these two outcomes, the spins would be opposite, well, definitely more than half the time, somewhere between 55 and 100% of the time, right? That's assuming there is hidden information. But if you actually do this experiment, you get opposite spin exactly 50% of the time, which would seem to indicate that there is not hidden information, which maybe goes back to the original case of, well, maybe there's somehow information being passed faster than the speed of light. Right? So I'm going to jot that down here. Okay. Spin information from entangled particles I'm going to throw in the word possibly. Possibly travels faster than light. Okay. Okay. So more on that in the middle, and then. Right. So a big part of the story is, of course, this John Bell 1964 experiment. Seems to rule out hidden information. Right. And one more point that you guys catch up to there. Right. Right. So that, I mean, seems to conflict with relativity, theory of relativity. I mean, that's why it's bothered Einstein too, right? Like one of the rules in theory of relativity is you cannot travel through space faster than the speed of light, right? There've been a couple of examples you guys seen like on the periphery that kind of push against that idea, right? So one example is just the expansion of space itself, right? Because of how space expands uniformly. If you get two galaxies far enough away from each other, they will be moving away from each other faster than the speed of light, but it's not because they're moving through space. So it's like, okay, so relativity is still safe, right? Just space expanding between faster than the speed of light, right? And then this is the other one that kind of tests the limits of theory of relativity, right? Is there some information that's being passed between these particles that is instantaneous, right? And what implications would that mean, right? Does space appear to be all spread out, but it's not really as much as it is, right? What does that mean? Now, maybe the catch that possibly still protects relativity from this point of view is that it's all random information. Random information. Okay. So if we were some number of light minutes from Mars, say we send an astronaut to Mars and we're communicating back and forth, sending emails through space, right? Probably be doing one day, right? But there's like a several minutes delay, right? Could you take advantage of this quantum entanglement and say, hey, I can figure out how to send an email and it gets to there in like less than a second? And everybody agrees that no, you can't do that because the email would be not random information, it would be actually not random, right? So still, so you can't send an email faster than speed. Okay. All right, you guys good there? Okay. All right, next one, fate or free will. Here, let's go active video for this idea here. All right. All right, so yeah, this is a question. Maybe this question comes up in your other classes too. You know, maybe books you read, or maybe in a psychology classes. Is everything that's happening like fated to happen, or like if you make a decision, how much of that decision is yours, or how much of it is governed by just like nature and nurture that you have some biology and you grew up in some cultures, right? Right, so here, I'm going to draw a billiards table. Make a Newtonian analogy here. Okay, so say we got this billiard table. Here's the pockets. 6 pockets. Right? Let's put some billiard balls on this pool table. Right? I'm gonna strike this one with the cue stick right here. Bam. Right. So the Newtonian perspective on this is that here. So call this Newtonian determinism. Implies that the future is fixed. And the reasoning goes, say like you're playing billiards, right? And you strike the cue ball. Now, once you strike the cue ball, everything that's about to happen in the next few seconds is determinable, right? It's just a matter of time until clock runs forward and everything plays out, right? Like if you know the masses of these balls and what type of collision it is, it's pretty close to elastic. So we got collision physics. If you know what angle you're striking these things, right? And if you get good at billiards, you can send any ball to any pocket, right? If you know what you're doing, right? Strike it just the right speed, right angle, right? Well, could you take that like more generally, right? I know it's like chaos theory and that, but besides that, in principle, if you knew the position and mass and velocity of like every particle in the universe, okay, could you maybe like in principle determine what's going to happen down the line? Right? And Newtonian determinism says, yeah, that would be the case. Well, how about like your own decisions? Like I want to go eat a sandwich for lunch or something, right? Is that something that's your own choice? And Newtonian determinism says, well, how are you making that choice? Well, you're making it, say, with a brain, and your brain is made out of matter, which is tied to the physical laws of the universe, right? You get down to it, it's electrical chemical signals being set in your brain. Right. So, you know, what made you hungry in the first place? It made you want a sandwich. Oh, right. Well, maybe your blood sugar got low, and so triggered some chemical biological response that made you have the thought to go eat lunch in the first place. Right. So how much of your decisions are actually yours? Right. There's some crazy experiments with this too. Here, yeah, I think I got time here. Gosh, a minute. So I might show this to you guys one day. This experiment where, say, like there was this box in front of people, right? And they had their brains wired. I think it was like an EKG or some of them read brain signals. And all they were supposed to do, very simple, is just press a button. It's like, okay, they got a box with a button, very simple, right? And they press it 10, 20, 30 times, and the machine is learning how to read their brain signals to predict when they're gonna press the button, right? And eventually gets pretty good, right? So they go in to press the button, and then the machine, when it recognizes it, sends off this buzzer tone, and then it's supposed to be a race between them versus the machine. Can they press the button before the machine knows they're going in to press the button, right? And then they can't do it, right? So they go to press the button, the machine knows, and it goes sends a signal like, I know you're going to press it because I see the brain signal. Clearly, you're going to go press the button, right? So then now the machine's getting better and better at reading their brain, right? Right. So now they got to try to figure out how are we going to take out those machines. So they go and like get ready, and then like they can never beat it, right? And after a while, they're sitting there like staring at this button, like, okay, when am I going to press it? How am I going to take out this machine? The machine just starts sending the buzzer like, it's like, oh, well, I wasn't even going to press it all. I'm just sitting here trying to figure out when I'm going to do it. But the implication, like one of the interpretations of this is that, well, maybe actually you were thinking of pressing the button, you were about to, but it was a decision from your subconscious that hadn't yet bubbled up to your conscious yet. So you just hadn't become aware yet that of the decision that had effectively been made for you from your subconscious, right? So what's in charge, or what decisions are you making, or how much in control are you of anything you ever do, or whatever decisions you make? And that's a really open question. It's possible that we mostly have free will, and it's also possible that we have very little free will, and it's mostly an illusion, right? Or depending on who you ask or what experiments you look at. So back to here, if you take Newtonian determinism to its logical end, then it would seem to imply that we're just all cogs in a machine that's just playing out, right? And everything's just happening, right? Newton believed that, probably, or at least his view of the world would indicate that. Einstein believed that, right? That we're all just part of something that's just playing out, right? But you bring in quantum mechanics. Quantum mechanics. See, I'll say at least possibly allows for, well, uncertainty or free will, maybe from this point of view, right? Because what type of physics do we have to make sense of the world, right? It's basically two camps of physics. There's really these two different sets of rules, right? One is the expansion on Newtonian mechanics is general relativity. That's like the updated version of this, right? And then down to particle size, you got quantum mechanics, which is probabilistic, and there's uncertainty, right? So now, is it possible that what allows us to have make decisions is maybe in neither of those camps, and maybe it's some third set of something we just don't know how to measure? I mean, maybe that's possible too, but in the realm of physics that we know, that's maybe the frameworks we have to even analyze that question. Okay, next one, let's do this one real fast. 4 fundamental forces. Right, so this is a setup to the next part, which is standard model, which we'll have to do tomorrow, right? But here's the 4 fundamental forces of nature. Right? I'm just going to list these out here and then tell you guys a little bit about them. Okay? We got gravity, gravitation. We got electromagnetism. Right, and then 2 nuclear forces. So strong nuclear force and the weak nuclear force. Okay, so here, I'm just going to jot those down and tell you guys a little bit about those while you're writing down. Here they are, same ones, this poster. Okay, right, so in this class, we mostly care about the first 2. Right, so universal gravitation, you guys learned last semester, F equals GMM over R squared. And then electromagnetism is almost everything else we care about in this class. Normal forces, friction forces. How can I pick up this pen? Oh, because it's electrons in my hand, electrons in the plastic of the pen, electrons versus electrons, pick it up. That's electromagnetism. Okay, right, now, how do you make sense of the structure of the atom? Like, why would all the protons hang out in the nucleus? Well, that's strong nuclear force, right? Because that would go against an EM view of the world, right? Right, and then weak nuclear force has to do with governing radioactive particle decay, right? Now, an extra detail about this before I move on is we're about to go into standard model. Now, the standard model of particle physics was laid out, I think, in the 1970s. Right? Actually has a space for only 3 of these two nuclear forces and electromagnetism, but not really for gravity. And actually, if you ask Einstein, I think Einstein laid out the case that gravity is not really a force at all. Like really, there's only 3 fundamental forces, and that's these 3 here. But normally textbooks say, what are the fundamental forces? Oh, there are 4, and there's these 4 here, right? Here. So Einstein's case that gravity is not actually a force, it's just an artifact of curvature of spacetime. Here kind of goes like this. Because if you're in a car and you step on the gas pedal and accelerate forward, you can feel the seat pushed against you. You feel that force causing acceleration. Same thing, you hit the brake or turn the steering wheel. Right? There are forces that cause acceleration, you can feel that. But if you blindfold yourself and jump off the building, then while you're in free fall, you don't actually feel an acceleration. You feel identical to an astronaut in deep space just floating around. In fact, it's physically identical. It's not really a way to tell to distinguish the two, right? And so he said you should actually consider the from the frame of reference of the person who's in free fall, right, that it would be indistinguishable from being in deep space. Well, okay, I know I'm up against the bell here, but yeah, long story short, there is that you can make the case that gravity is actually not a force here, which standard model might actually agree with. It's actually an artifact of the curvature of spacetime. All right, so we'll hit pause right there on that adventure and continue that tomorrow.